calculations. Oh no, I was dreading this point. This whole time he kept saying calculations and math and numbers. Oh no, what am I going to do? Calculations for polarimetry is not supposed to be very difficult. It is somewhat of a straightforward process as long as you do a couple of things the same way every single time, and numbers just go in and you crank out the value on a calculator. And sometimes if you've got automated equipment, it will actually do the calculation for you and it will pop out this value from the equation. We do not have our instrumentation set up that way, and the reason is because we want you to do it, my friend. We want you to go through the motions of solving and pushing numbers into a calculator and understanding where these values come from, because that's part of this whole situation. So in this video, we're going to talk about measuring and calculating a value that we have to report when we do polarimeter reads. All right, so here we're going to see an equation, and that equation is over on the right-hand side of the screen, and it's a bunch of squiggly lines. I see a little squiggly in a bracket with a T and another squiggly equals squiggly over L with a squiggly. Okay, so these values, these variables have to represent something, and we need to talk about what these things are. And then after we understand what they're supposed to represent, then we can start going in and plugging numbers into these types of calculations. First off, I think one of the ones that we know right off the bat is going to be our T value or our T variable. Our T variable is our temperature. So this is a temperature readout, and this is a number that we want to pay attention to because, again, most of the time it's 20 or 25 degrees, but it could be something else, and I don't want to take anything for granted, and I always just want to double check it. Is this value that they want me to report, is it in reference to 20 or 25 degrees? And if not, I need to take measures to correct for these values because of that. Next up, something else that we also talked about already is this little squiggly thing down there. That is going to stand for the wavelength, and the wavelength is going to be nanometers. And we said 589 nanometers was the wavelength that the sodium D lamp provided. So depending on the bulb that's used in the polarimeter, we could be getting values or measurements that are obtained by not using 589 nanometers. So we want to make sure that we at least pay attention to that as well. For the most part, it is 589, and for the most part, we said that a D is stamped there, and that D means sodium D lamp, and that D represents 589 nanometers. So these two numbers we've already talked about already. Some of the others, though, not so much. So I think one of the easiest ones to pick out now is in this equation, there's an L that is here. And that L is the length of the sample tube that you have used in the laboratory. These tubes can come in different lengths. They can be really long and they can be really short. It just really depends on what you need and why you need it. So very often in the USPNF monograph, this sample tube is going to be provided in units of decimeter, and decimeter is typically a 1 decimeter tube. There are times that it will tell you to use something else, and that really depends on the sample. How concentrated is the sample? How weak is the sample? How does it respond to turning of the light? All of these play a factor in the size of decimeter tube that the USPNF wants you to use. By default, though, if I had to have a go-to, the default is 1 decimeter for the tube. And that makes this very easy because that means that in this equation, whenever I see the L, that L is a 1 unless I've used something different. So in our lab, we have 1 decimeter tubes, and we also have 0.5 decimeter tubes. And it really just depends on what we need at the time. So we'll be flip-flopping back and forth with that sometimes, but the go-to here is 1 decimeter in total length. Next up is this little squiggly on top. This little squiggly on top, that's alpha, And that alpha is going to stand for what we call optical rotation. And this is an optical rotation. Yes, it is. But this is an observed optical rotation. So it is what I obtained in the laboratory. So when I made this sample, I put that sample in my tube, and I put my tube into the polarimeter, and I closed the door. And then I had that polarimeter to make a measurement. That measurement was a measurement that I observed because I made that sample. I placed it in that sample compartment. I placed it into that instrument, and that is the observed reading because of that. That is alpha, and alpha goes on top. So this is my lab measurement, in other words, okay? And then the other thing that we've kind of talked about, you might have forgot it though, was the P, and that P is actually rho. And rho is going to stand for density here. And density is going to be in terms of grams per milliliter. So that is the preferred concentration that we like to use in these calculations. We don't use things like molarities or normalities or part per millions or part per billions or percent by blah, 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 blah. I mean, there are just tons and tons of different options that are out there. Gram per mil is going to be the concentration that we're after most. So what happens is that I'll take my lab number that I get, and then I'm going to divide that by, and in parentheses, 1, because most of the time it's 1 decimeter, times the density of the liquid solution. But the problem here is that this equation is only for something that we call a neat liquid. That's what this is. So a neat liquid is something that really is a liquid on its own. I probably didn't have to use any type of solvent at all. And I've just literally put that liquid into the polarimeter cell and called it a day. Right? I mean, that's really all that I have to do here. So there was no solution that I had to make. I didn't have to weigh out grams of something and dissolve it in water or dissolve it in an acid or dissolve it in a base or dissolve it in a buffer. I didn't really have to do any of that sample prep at all. It was just simply, let me get some of this liquid, let me put some of this liquid into a polarimeter tube, and let me just run it. So what you're going to see, or probably what you've already done, is that in our lab, a neat liquid would something be like essential oils. All right. This is a typical kind of run-of-the-mill. It's already a liquid, no solvent needed. Just put the essential oil in there and run it. And then whatever number shows up on the screen, you're going to write that number down. So in order to do this calculation, though, you're going to have density of that liquid solution. So very often a density or specific gravity measurement is going to accompany this, and there's probably a very high chance that that is also going to be included in the monograph that we have to follow. And that's one of the reasons why. Not only does that density help confirm it is what it is, but that density is also going to be used in this particular type of equation. So that way we can solve for our real reported value. Also notice that this is straight up density. It is not specific gravity. So specific gravity is very often reported in the terms of, let's kind of look at that number alone and let's report specific gravity and see if it matches. But this really by far is a density readout, not a specific gravity readout. So if I take my lab data and I divide by parentheses 1 for the sample cell length times rho, which is the density of the liquid, and I hit enter on the calculator, what I'm going to end up with is bracket alpha. And bracket alpha is something called specific rotation. And that specific rotation is a value, and that specific rotation is corrected for the sample cell compartment size as well as the concentration of the sample that you place on the inside. So these are what's going to be reference book values. So the reason that I go through this motion is because very often we're required to do this calculation. But more so than that, when I look up optical rotation in a reference book, or when I see the optical rotation listed in the monograph, it is talking about specific rotation. and therefore a correction is going to have to be needed in order for me to possibly get that number that they state in that document. And that calculation is based on the lab number divided by sample length times concentration or density for a neat liquid. All right. So that's going to be how we calculate specific rotation for a neat liquid. You need a density value. That density value goes into the equation. You times it by 1 most of the time, unless it tells you otherwise. And then you take your lab number, divide by that total. And that answer is specific rotation. Hopefully that will match the monograph, and hopefully that will match its reference books if you begin to look it up. All right. Next up, well, what if we don't have a neat liquid? What if we've got a solid that has been dissolved in a liquid solution, right? I mean, what if that goes on? Okay, well, that's fine. That's not a big problem at all. And the reason is because the equations are pretty much identical. So again, for solids that are dissolved in some type of solvent, we have to make a solution for them. And this equation is very similar to the one that we just talked about for what we called a neat liquid. Again, a neat liquid is liquid at room temp, or whenever we do the measurement, and there's no solvent added, we're not weakening it down or anything. And we had this row number, and that row meant density. It was the density of the liquid. So when we take a solid and we dissolve it in liquid, we kind of have a row number, but it's not really a density value at all. But the unit or the concentration is still grams per milliliter. And this is grams of the solute, which is the solid that I'm trying to dissolve, per milliliter of solution. So yes, there is a calculation that I have to do on the side. I have to do a concentration value of it. But as long as I know how much I've weighed out, and as long as I know how I dissolved it to the total volume of, I'll be able to calculate that value without an issue. So that is the C for sample concentration. And I'm seeing that that sample concentration is right here. So notice it's not a row value, it is a density, or the density value that was there, it is a concentration value that's there. Density is gram per mil, and concentration is still going to be used in grams per milliliter. All the other variables are the exact same. So this is the specific rotation. That specific rotation is what's going to be found in a reference book with a sodium D lamp and at a particular temperature. And this is the observed rotation. So this is what I find in the lab. And then L is still the length of the sample tube. It's just the C variable that is here instead of the row variable. So grams per mil. And as long as I have an idea of how the solutions are made, I'm going to be perfectly okay. So these are actually the most common versions of solutions that are prepared in the lab that we run on a polarimeter. We do have neat liquids, but solids dissolved in some type of solvent is often kind of the more run-of-the-mill type of prep work that we do for a polarimeter or optical rotation read. So again, don't let those questions trick you. There are two different versions of this equation, though, on the screen. This one at the top is, of course, the most common, but here is for a sample solution that is gram per gram. This works, but it depends on really how we are reporting the values and what the requirement is in terms of the monograph and on the report. This is, again, pretty similar. We get specific rotation. We get optical rotation at the top. We get the length of the polarimeter cell. But because this is gram, we need to go from milliliter to gram now. And in order to go from mil to gram, you really do need density in order to convert one from the other. And that's what you're seeing here. So rho is included in the density, and then CW is going to be concentration really in terms of gram per mil. So that density will allow you to calculate in terms of gram. All right. So that's a little bit about the equation that we can use in a polarimeter read and allow us to calculate what we would call specific gravity. So what I want to do is go through and maybe just give you an example problem, and that way we can kind of figure out like how is this going to work, maybe some values, and go through the motions of some calculations. I think that's going to be good for us. And here we go. Let's see. Example number 1, part A. A lab worker measured 3.451 grams of sucrose and dissolved it in a volumetric flask. He brings the total to 50 mils with water. After blanking the instrument with water, he measures the rotation using a polarimeter cell that is 0.5 decimeters. He obtained a 0.61 reading. What is the specific rotation of the solution? Okay, not a big deal. Specific rotation is alpha bracket. And we just now realized that to solve this equation, I need the observed lab rotation up on top, and it says he obtained a 0.61 reading. All right, so 0.61 goes there. See, that's not hard. And then down below, it said that we needed an L, and that L is typically the length of the tube. So the length of the tube's given. A polarimeter cell has 0.5 decimeters. We said that most of the time it is 1, but, you know, here we do something a little different. That's okay. It's not a big deal. I'll just put 0.5 there instead of a 1. And then next, we multiply, because this is a solid that has been dissolved in water, we need to figure out the concentration. And the concentration should be provided in gram per milliliter. So if I take the amount of grams that this person weighed out, 3.451, and we divide by the total volume, which was brought to 50, then this is going to give me the concentration in terms of grams per milliliter. All right, so I'll take 3.451 and I divide this by 50, and then I hit enter, and I get a concentration of 0.06902. So 0.6902. All right, so 0.6902. So you know me by now, I like to do things in little bitty baby steps, and I'm going to clean up the bottom first. So that's not a big deal. I'll take 0.5 and I'll multiply by 0.06902, and then I hit enter. Bing! There we go. So 0.3451. All right, so 0.3451. That cleans up that bottom a little bit, makes my math a little bit easier to key into the calculator. So my specific rotation equals 0.61 divided by 0.03451. All right, so 0.61, and then we'll divide by 0.03451. Enter. Ta-da! Here's our specific rotation. So that specific rotation says 17 point, let's round it to 2 decimal places. So 17.68. All right, so 17.68 is my observed rotation. This is a positive number. I know it's a positive number because the laboratory value was understood to be a positive. If it was left-handed rotation, then it would be a negative in front, but this is a right-handed rotation, so very often they just don't put the plus, or it's just assumed that it's going to be there. Part B says, if this was a calibration standard, does the sample pass or the instrument pass? So we need to talk a little bit about calibration standards here, and we're going to come back to this example problem and finish that when we do. But while we're on a roll, we might as well do another example. So here we go. Example number 2, specific rotation of a substance should be 64.95. An analyst measures a lab sample on a polarimeter using a 1 decimeter cell, and he obtained a reading of 38.51. What is the sample's concentration in gram per milliliter? Okay, not a big deal. I just need my specific rotation equation, and this is specific rotation equals the optical rotation divided by the length of the sample cell times the concentration of the sample. And that's what we're trying to find in this example. So if I just go in and start plugging in my numbers, specific rotation of a substance should be 64.95. Okay, that's based on textbook value. So that is my specific rotation, the one in brackets. So 64.95 equals. An analyst measured a lab sample on a polarimeter using a 1 decimeter cell. All right, well, that's the length. So a 1 is going to go down there at the bottom. And obtained a reading of 38.51. That is the laboratory reading. That is what I observed. That is what I obtained when this sample was ran. So that is alpha that goes on top. So 38.51. And the question says, what is the concentration in terms of gram per milliliter? And that's perfect for me because concentration is typically gram per mil. Nothing that I have to do in order to switch that problem or that value up. All right, so we need to simplify this down a little bit. I'm okay. We'll take it baby steps. 64.95 equals 38.51 divided by 1 times C, which is C. So now we've got to figure out how on earth do we solve for C? How do we get it kind of isolated so we can solve for that variable? Well, the rules of math will say, oh, well, you got a number in the denominator, so we're going to have to multiply each side by that value. So we'll multiply by C and we'll multiply by C. So those kind of cross out and we get 38.51 equals, this is 64.95 times C. And then we still don't have C by itself, but we get rid of all those fractions and those denominators that we don't like to see. So in order to solve for C, we got to get rid of everything around it. And part of what's around it is 64.95 times. So we do the opposite of. So we're going to divide by 64.95 to each side. In other words, we just kind of flip-flop the C and that value around. So that goes away and we're equal. C equals 38.51 divided by 64.95. So we'll key that into the calculator. We'll do 38.51 and we'll divide by, and this is 64.95, and we'll hit enter. Ta-da! So we get a concentration as far as grams per mil goes of 0.59, and we'll keep, I don't know, 3 digits. So 0.593. Again, I'm not really after significant figures. I'm not after any of that kind of mess. It's just a simple number that shows that you can do the calculation. That's what these are all about. All right, so 64.95 is the specific from a reference book. 38.51 is the value that I got in the lab when I ran the sample. And then 1 is the length of the polarimeter cell, and we solve for C. C is the concentration, and C is always in terms of gram per mil, and that's exactly what this particular unit wanted, grams per milliliter. So whatever number I get from the equation and the calculation, that's the number that I'm going to report. So 0.593. All right, next up, we're going to look at example number 3. A laboratory person built a Cal curve using a series of standards and polarimeter values, and she obtained the following information. So standard number 1 was a 3%, and a 6, and a 9, and a 12, and a 15. And those standards ran 5.9, 11.9, 16.89, 21.48, 26.43. And then next, she got an unknown sample. She didn't really know what that was, concentration-wise, and she got an optical rotation for it that's observed, and that was a 13.43. And it says, well, what is the sample's concentration in terms of percentage? So this is a way that we can revisit a couple of topics here. One, we are building a calibration curve using polarimeter data, and we can do that quite easily. Just like any other calibration set, we just need to establish a relationship between the concentration and the signals from the instrument. So it looks like she did a series of 5 standards. They went weaker and then stronger, 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 and then those optical rotations went more and more and more, because as it gets stronger, there's more stuff, and as more stuff is present, it turns a lot more, so that makes sense. So it looks like we're going to have to use Excel in order to answer this question. So let me pull up Excel and we'll go through the motions of plotting a calibration curve. Okay, so I've got my handy dandy Excel spreadsheet popped up here, and I just need to type in some numbers. That's really all I've got to do to solve this type of problem. Watch how easy this is going to be. 3 and a 6 and a 9 and a 12 and a 15. That's not very difficult, right? And then on the y-axis, I need to pop in the values that I got from the polarimeter. So 5.9 and 11.9 and 16.89 and 21.48 and 26.43. All right, that's as hard as that's going to be. So now I've got the raw data that's entered into the spreadsheet. I need to make a calibration curve. So this is something that we have talked about before, and we'll go through the motions again. I'm going to pretend like you've never seen it, because you probably didn't watch those videos, and probably because you didn't pay attention, and probably because you didn't take notes, and probably because you didn't study, and probably because you probably failed those quizzes at the time, and that's okay. But if I highlight the data, there we go, 3, 6, 9, 12, and 15, and then there are the optical rotations from the machine. I'm going to go up here to the top of Excel. I'm going to do Insert, and then I'm going to come over to the chart area, and I'm going to click the chart. And there's going to be a few options that will show up in the scatter type of chart that I've just chosen. And the one that I want is the one that has the points or the dots that are just scattered. So there they are, the X and Y axis, just a couple of points, and that is about it. So I'm going to click on that option, and hopefully, oh no. All right, so let's go through this motion again. My Excel spreadsheet just canceled each other out because I was bragging about how easy this was. Probably that's what was going on. I know that's what was going on. All right, so here we've highlighted the X and Y axis. I'll do Insert, and then here under Charts, I'll click, and then I'll click Points, and there we go. Look at how beautiful that little calibration chart is. I probably did something real good, and I almost made a straight line. So a couple of things that I want to talk about before we go through the motions of finishing this calibration curve out. Number one, I've plotted the raw data from the question, and that's exactly what we needed to do. But I have left out something, and I did this on purpose because this is what most people do, because they only focus on the data that's given in the problem. But we have to understand that this instrument was blanked, and it was blanked using the solvent that I dissolved these solutions in, or that I made these solutions in. So that blank should also be included in the calibration curve, and we hope that the blank goes through the point or something close to the 0.00. And I've left this out. So look at this. I've did all of this work, highlighted, did the chart. I'm going to click out of that. Oh gosh, it's so pretty. And then I'm going to be like, oh no, I forgot my 0.00. What do I do? All right, well, I'm just going to go in and I'm just going to add it. So 0 and 0. It doesn't have to be in order. As long as all the points are there, that's all that matters. And then over here to the left-hand side, I'm going to click a data point, and notice that when I do that, the cells are highlighted here to the left. If I forgot to add a point and I want to now include that point even after the graph is already made, I just click the data set is highlighted, and I click the box down here in the corner, and then I drag down. So I drag down the blue one and I drag down the purple one. And when I do that, ta-da! 00 shows up, and it's already in the graph. So now when I click off of it, that is one of the points that it has plotted, and it looks pretty darn close to 00 for me. At least this line is going to look pretty close to 00. So here I'm going to click on the data points again, and I need that equation. So I'm going to right click, and I'm going to add a trend line. And when I do that, the prompt shows up over here to the right hand side, and I'm going to display the equation and display the R² value. So I'll close that screen out so I get my bigger Excel portion of the screen back. And here is the equation that I need in order to solve this problem. So it looks like to me that I'm going to take 1.7512x plus 0.6324, and that is the equation that I need to use to solve for my unknown concentration. All right, now again, notice it didn't go through exactly 0, 0. That dotted line is just a little bit above, and that's okay, but it's at least close. And that means someone did their job the proper way and blanked this machine the way that they should have. All right, so here's the equation that came from the calibration curve. Now, the sample ran 13.43. This was the observed rotation. And the observed rotation, ladies and gentlemen, is the y-axis. So that means I need to take my 13.43 and I need to plug it into the y variable. So 1.7512x plus 0.6324. So this is the value that we need to use in the y variable, and x is the concentration. And that concentration I know is x because that was plotted in the x column and on the x-axis of the graph, so the x variable represents the percentage. And that's what this question wants. What is the sample's percentage? What is its concentration? All right, so as I go through, I just kind of baby step this along the way. I always like to do that. So I'm going to take 13.43 and I'm going to subtract. I need to get x by itself. So there's a number out here that's on the extremities. Before I worry about the one that the x is attached to, I got to get rid of all the neighbors first. So that is plus 0.6324. I'm going to subtract 0.6324, and then I hit enter, and I get 12.7976. All right, so 12.7976 equals 1.7512x. And now I need to solve for x. So this is 1.7512 times. So I need to do the opposite. I need to divide. So 12.7976 divided by 1.7512. And then I hit equal. And my concentration looks like it's going to be 7.31. So x is equal to 7.31. Again, I'm not really concerned with significant figures. That's something that I'm not worried with. I'm more worried and focused on the process of getting that number first. If I go back to the example problem, I'm going to see all these concentrations are given to me in whole numbers, and that probably means that I need to report my concentration in whole numbers as well, but that's a different story for a different day. But 7.31, something really close, you're going to get full credit, and this is how we use a calibration curve with polarimetry and optical rotation data in order to solve for an unknown concentration as well. So two different ways. I can use my standard, hey, let's take my one reference or my optical rotation and C times L. So I can use this equation and solve for concentration, but the problem is that I'm relying just on a textbook number, and that is it. The other way is to build a traditional standard calibration curve and then use that equation y equals mx plus b in order to solve for the concentration. And that way, you probably are going to get a better number if you follow through, because this is normally how calibration curves, how samples and standards are ran and made and processed in a laboratory. So one is more or less spreadsheet work, and the other one is more or less a little bit of algebra, very quick check of what those concentrations might be. So in the next video, won't forget, we'll go back to example 1. We'll talk about part B. But we've got one more example, and it says an essential oil was analyzed on the polarimeter. The lab worker pipetted 3 mils of the oil on a balance to get the density. The mass of the 3 mils was 3.8923. Afterwards, they analyzed it on a polarimeter, and they obtained a reading of 6.98. What is the specific rotation of the essential oil? So in the next video, we'll pick up with this example problem, and we'll work through it. I'd like for you to, though, do this on your own. See what kind of number you get. See if you're going to match my answer when we come back and watch it in the next video. Then we'll talk a little bit more about the machines, and we'll come back to the second part of example number 1.